I wanted to work through a problem that involves capacitors and a circuit containing series and parallel capacitors. In this problem, we're going to firstly work out the equivalent capacitance of the network of capacitors, and then we're going to figure out for the individual capacitors the voltage across those capacitors, potential difference across those capacitors, and the electrical charge on those capacitors. So that's basically the plan. Now, the circuit is shown in this little sketch here. We've got a 9-volt battery that supplies a potential and supplies charge to the circuit. And then we got an arrangement of 4 capacitors shown here. And you'll notice that these 4 capacitors have different values. These values are in units of microfarads. So we've got C1 on the left, 8 microfarads. C4 on the right is 8 microfarads. Then downstairs and upstairs here, we got a 2 and a 6 microfarad capacitor. Before I go ahead and calculate the equivalent capacitance and the voltages and the potentials, I'm actually going to draw an equivalent circuit to this arrangement of 4 capacitors that will help us, assist us as we work through the problem. So in this equivalent circuit, I'm going to combine these 2 capacitors that are in parallel with one another. So these 2 capacitors that are in parallel, C2 and C3, can be replaced by a single capacitance, I'll call it C23, that has a capacitance that's simply the sum of the 2 individual capacitances. So C23 will have a capacitance of 8, 2 plus 6 microfarads. So let me draw that circuit. So here's the new circuit. It now has 3 capacitors in it. The 3 capacitors are arranged in series across the 9-volt battery. And the 3 capacitors all have the same values. They're all 8 microfarads. So let's go ahead with the calculation. We're going to start with calculating the equivalent capacitance of the entire arrangement of capacitors. The rule that we need here is that the reciprocal of the equivalent capacitance, the inverse of the equivalent capacitance of these 3 series capacitors, is simply the sum of the reciprocals or the inverses of the individual capacitors. That's the rule for combining series capacitors. So let me write that down. C equivalent is my equivalent capacitance. And I'm thinking about the reciprocal of it here, the inverse of it here. And that's simply equal to the sum of the reciprocals of the individual capacitors. So C1, C23, and C4. Well, each of those individual capacitors is 8 microfarads. So the reciprocals are each 1/8 inverse microfarads. So the sum of the reciprocals is 3/8 inverse microfarads. And if we just take the reciprocal of that, that gives us the equivalent capacitance. So the equivalent capacitance of the entire network is the inverse of 3/8, which is 8/3 microfarads. Okay, so now let's go ahead and calculate the voltages across the 3 capacitors in this equivalent circuit here. So that's C1, C2, 3, and C4. Once I've done that, I'll calculate the voltages across the other two individual capacitors, which are C2 and C3 upstairs here. So in this particular case, our equivalent circuit contains three equal capacitors. They're each 8 microfarads. They're each identical capacitors. If you apply a voltage across 3 identical capacitors, they're going to share that voltage. And because they're identical capacitors, they share it equally. And so that's an important idea, concept I can use here. Because I've got 3 equal identical capacitors, they will each get the same share of the 9 volts. Let me write that down. So V1, which is the voltage across capacitor C1, will be the same as V4, which is the voltage across C4. And that'll be the same as the voltage across this equivalent capacitor C23, which I'll call V23, because they're all identical capacitors, so they're all share equally. And because there's 3 of them, they therefore each get 1/3 of the 9 volts. So 9 volts supplied by the battery divided by 3, shared across the 3 capacitors, is going to give us 3 volts. So that's the voltage across C1 on the left. It's the voltage across C4 on the right. It's the voltage across C23 upstairs here. Finally, we want the voltage across the individual capacitors C2 and C3. There, the rule is that the equivalent capacitor and the individual capacitors in a parallel arrangement, not a series arrangement now, parallel arrangement, they all have the same voltage across them. So the same voltage is across C2, 3, as it is across C2 and C3. So finally, the voltage across C2, I'll call it V2, is the same as the voltage across C3, because they're in parallel, and it's the same as the voltage across their equivalent capacitor, which we called V23. And V23 was 3 volts. So V2 and V3 across C2 and C3 are also 3 volts. So actually, in this special circuit here, every capacitor has the same voltage across. Every capacitor has 3 volts. Okay, so finally, let's calculate the charges on the plates of the individual capacitors. And to calculate the charges on the plates of the individual capacitors, because now I know their capacitance and I know their voltages, I know their potential differences, I can just use that relationship C equals Q over V, or I'll be using that Q equals CV to figure out the charges on the plates of each individual capacitor. So for example, for capacitor number 1 on the left, we'll call its charge Q1, and it will be equal to its capacitance times the voltage across its plates. And we know the capacitance, it's 8 microfarads. We know the voltage across the plates, it's 3 volts. And if I multiply 8 times 3, I'm going to get 24, and that will be 24 microcoulombs of charge on its plates. We can do the same thing for C2 upstairs here. The charge on its plates, I call it Q2, is its capacitance times the voltage across its plates, C2 and V2. And in this case, C2 is 6 microfarads. V2 is 3 volts again. So we got 6 times 3, that's 18. And the units are microcoulombs. And so on and so forth. So for capacitor number 3, its charge is C3V3, which is 2 microfarads times 3 volts, which comes out to be 2 times 3 is 6 microcoulombs. And finally, for the fourth capacitor, the one on the right, its charge, Q4, is C4V4, and C4 is 8 microfarads, V is 3 volts again, so this is also 24 microfarads, microcoulombs of charge. Anyway, that problem was a walk through, a stroll through, or run through, an electrical circuit involving a network of capacitors over which we'd applied some voltage from a battery. And we first figured out the equivalent capacitance of the whole arrangement. And once we figured out the equivalent capacitance of the whole arrangement, we had all the information we needed to figure out how voltages were shared amongst the individual capacitors in this parallel and series network, how the charge was distributed over the plates of the individual capacitors in this series and parallel network.